So now we will talk about the rotation gate. So let's first define what a rotation operation or a rotation gate is in continuous variable quantum computing. So you may have learned about rotation gates in the discrete way, in the discrete paradigm. There we can write it as e raised to I phi sigma cap, something like this. In the same way, the rotation operators in the uh, continuous variable quantum computing paradigm is given as r cap phi equal to e raised to I phi n cap, where this operator is known as a rotation operator because it rotates the coherent state about the origin in the quantum phase space. I'll show you uh, in a few minutes. So, when a rotation gate acts on a fock state, so let's calculate what it gives. R phi acting on n is equal to, we open the exponent in the Taylor series, n cap plus I phi square by 2 factorial into n cap square and so on acting on n. This will give us n plus I phi n n plus I phi squared by 2 factorial n square n plus so on. Okay, so now this gives us equal to 1 plus I phi n plus I phi n whole square by 2 factorial plus so on acting on n, and this gives us equal to e raised to I phi n into n. So this is what the rotation operator when it acts on n gives us. We get this extra phase factor and nothing else when it acts on the fock state. So now let us calculate the operation of rotation on the coherent state. Rotation on coherent state. Okay, so that means mathematically we want to find r phi, r cap phi acting on alpha. So how do we do that? So for that you will uh, need to write alpha in the Fock basis. So this is e raised to phi I phi n cap e raised to minus half mod alpha squared summation n equal to 0 up to infinity alpha raised to n divided by root of n factorial into n get n. So this is minus half mod square alpha mod square exponential uh, summation n equal to 0 from 0 to infinity alpha raised to n by root n factorial, and your r e raised to I phi n cap will come and it will act on n, and this will give us e raised to minus mod of half into mod of alpha squared summation n equal to 0 up to infinity alpha e raised to I phi raised to n divided by root of n factorial into n. Okay, so now let us write alpha as mod of alpha e raised to I theta. We write it in the polar form. And let us consider some alpha prime, which is equal to alpha times e raised to I phi. That means it is equal to mod of alpha times e raised to I theta plus phi. We just substituted alpha here. And note that the magnitude of alpha and alpha prime is same, just that this theta plus phi is there, and there only phi theta is there. So if I say that this alpha and alpha prime, they represent some coherent states, let's say I have alpha and some alpha prime, then on the quantum phase space they will be given by two different positions. Let's say this is the position of alpha, then this is the magnitude mod of alpha, that is the distance from the center, and this is theta, the angle. And let's say that this is alpha prime state, then this is mod of alpha, that is the this size of this or the distance from the origin, and this angle is theta plus phi. Okay, so in that case we can write r phi mod of alpha equal to e raised to minus half mod of alpha squared, sorry, mod of alpha prime square, because alpha is equal to mod of alpha prime is equal to mod of alpha summation n equal to 0 to infinity alpha prime raised to n divided by root of n factorial into n. What we did, we wrote this alpha e raised to I phi here as alpha prime. So now this state is nothing but ket alpha prime. So we will see that when r phi acts on alpha, it gives us alpha prime. And this alpha prime is some state which is rotated about the origin. Uh, yeah. So if I act the rotation operator on the coherent state alpha, it rotates the coherent state alpha by the angle phi to some another coherent state alpha prime, which is equidistant from the origin. Okay, it's just that it rotates it about the yeah. So this is the what the rotation operator does on the coherent state, and that is why it is called as a rotation operator. So now let us derive some properties of rotation operators. So first of all, a rotation operator is a unitary operator, that is r dagger phi into r phi is equal to r phi into r dagger phi, and this both are equal to identity. How do I prove it? So just take e raised to I phi n cap, that is the definition of rotation operator. Take a dagger over it, e raised to I phi n cap. So this is equal to e raised to minus I phi n cap into e raised to I phi n cap. So using the Baker-Campbell-Hausdorff formula, this is e raised to I phi minus phi n cap, which is equal to or minus phi plus phi. That is also another way to see it. This is going to give us 0, so this is equal to some identity operator. So hence rotation operator is unitary. Now we already saw that r dagger phi is equal to e raised to minus I phi n cap, which is nothing but e raised to I minus phi n cap, which is equal to r of minus phi. Yeah. Now let us derive the next part. R phi 1 into R phi 2 is equal to R phi 1 plus phi 2. This is another property. Let's derive it. So this is e raised to I phi 1 n cap into e raised to I phi 2 n cap, which is equal to e raised to I phi 1 plus phi 2 n cap. We use the Baker-Campbell-Hausdorff formula, and because n and n cap commute, so this is the form that we will get. Okay, let me just write what the Baker-Campbell-Hausdorff formula says. That e raised to a cap into e raised to b cap will give me e raised to a cap plus b cap into e raised to commutator of a cap b cap by 2. Now, because this commutator is 0, both A and B are n cap, so this is just 1. So that is what we used earlier also and now also. Okay, now you can also see that the rotation operators are commute, they commute. So R phi 2, R phi 1, they commute. Let's check it. N cap e raised to I phi 2 n cap. I can just take this here because both the operators in the exponential are n cap. So this is e raised to I phi 2 n cap into e raised to I phi 1 n cap. And so we see that they commute with each other. Okay. Now let us derive some another important identity. R dagger phi a cap R phi is equal to a cap e raised to I phi. And R dagger phi a dagger R phi is equal to a dagger e raised to minus I phi. So these two identities are there. Let's prove. So first one is nothing but e raised to minus I phi n cap a cap e raised to I phi n cap. Let us use the exponential form of the Baker-Campbell-Hausdorff formula, and this will give us a cap minus I phi n cap a cap plus I phi whole square by 2 factorial n cap into n cap comma a cap and so on. Let's calculate this. So this is equal to a dagger a comma a, which is equal to a dagger a minus a dagger a, and this is nothing but equal to a dagger sorry a dagger minus 1 into a minus a dagger a. So what I used here is that a dagger commutator is identity. That is what I used here, and this gives us a dagger a minus a dagger a. And wait a minute, a dagger a. Okay, I need to write it properly. Okay, a dagger a minus a dagger a. So this and this cancels, and this is minus a. So minus a gets substituted here. So this is a cap minus I phi minus a cap plus I phi square by 2 factorial into minus of n cap a cap plus so on. So this gives us equal to a cap plus I phi a cap plus I phi square by 2 factorial into a cap and so on. So this is equal to, if we take out a cap common, This is e raised to I phi. So r dagger phi a cap r phi is this. In the same way, I leave it on you to derive what happens with a dagger. It's simple. Now let's calculate another property. I write down another property. R dagger phi x cap r phi is equal to x cap cos phi minus p cap sin phi, and r dagger phi p cap r phi is equal to p cap cos phi plus x cap sin phi. Okay, so let us derive this identity. First one. So this is nothing but r dagger phi a plus a dagger by root 2 into r phi. I have written x cap here in some particular convention. So I've taken out all the, what you can say, different units, etc. I've just made it in this particular form for simplification. But even if you write them, at the end of the day, you will get the same result. So r dagger phi a plus a dagger by root 2. This is the x cap quadrature operator, and I have written it in this particular manner. Then this is equal to r dagger phi a r phi divided by root 2 plus r dagger phi a dagger r phi divided by root 2, and this then gives us a e raised to I phi by root 2 plus a dagger e raised to minus I phi by root 2. So I write this in the, I open this up, a e raised to I phi. So this is a cap cos phi plus I sin phi plus a dagger cos phi minus I sin phi. Both are under root 2. So this can be written now as x cap cos phi minus I sin phi p cap by uh, taking this together and this together and using the definitions of x cap and p cap. I leave it on you to find the other transformation. You have to just use the same formulae. Then there is this another identity, r dagger phi n cap r phi. What does it do? So this is nothing but e raised to minus I phi n cap e raised to I phi n cap. Now because any a cap comma e raised to a cap is equal to 0, in the same way this commutes, and we can take it over here, minus I phi n cap e raised to I phi n cap, and this two will give me identity, so this is equal to n cap. This is what it does. Now, you may have seen that for the displacement operation, we had created some special gates for some special parameters out there. In the same way, with the rotation gate, we can create some special operations with the special parameters. So, one of such special rotation gates is called as the Fourier gate or Fourier transformation. So it is defined as f, which is equal to r pi by 2. So this we take as pi by 2, phi. The angle theta we take it as pi by 2. So this gives us e raised to I pi by 2 a dagger a. So what happens when it acts on the quadrature operators? So f dagger x cap f will give us minus p cap. So what you do is, in this thing, you just put this as pi by 2, phi as pi by 2. So cos pi by 2 is equal to 0, and sin pi by 2 is 1. So this becomes equal to minus p cap, and that is what we see here. In the same way, f dagger p cap f will give us x cap. So this is like Fourier transform of the conjugate variables, and that is why this is called as the Fourier gate. Basically, what I mean to say is that when f cap acts on the position ket, it takes r pi by 2. It is r pi by 2 alpha mod of alpha theta equal to 0 equal to alpha mod of alpha theta equal to pi by 2 equal to p. That means on the phase space, what it actually does is, so this is your x cap, this is your x position operator. So any position ket, any ket which lies on the x-axis is called of the quantum phase space is the position ket. Now I act by a rotation of pi by 2. So what it does is that it takes this from year to year. So this is nothing but a special coherent state where alpha is such that this is some mod of alpha and theta is equal to 0. So this is some mod of alpha and this is some theta equal to 0. So this takes it by an angle pi by 2. It rotates by pi by 2 and places it here on the y-axis. So any ket on the y-axis is a momentum ket in the quantum phase space. So it becomes some p. And if I write it in the coherent state form, then it is equal to alpha mod of alpha comma theta equal to pi by 2. So that is why it is called as a Fourier gate.